All right, this next section, 10.4, we're going to take a look at absolute and conditional convergence, and specifically alternating series, and what does it mean for an alternating series to either absolutely or conditionally converge. So an alternating series, here's an example of one. In this case, the word alternating just means switching or flipping and flopping, alternating in sign. So positive coefficient, negative coefficient, positive, negative, positive, negative, positive, negative, positive, again and again and again. So it doesn't actually matter if we begin with a positive or if we begin with a negative. That doesn't actually matter a ton. This theorem, however, may lead you to believe that it is very strict which ones are positive, which ones are negative, and based on the theorem, there is a certain assumption that is made, but regardless, if you do have a series that converges, then we do know that for any series that converges, we can take any number and multiply it. So if I have a convergent series that's alternating, I can multiply it by -1, which would then change the order of all of the pluses and minuses. So if your series is convergent, then you can change this order of the pluses and the minuses, and that doesn't actually matter. So what's really important here isn't so much the specific what we begin with, positive or negative, but rather that every other term, they're going to flip signs. So this is an example of an alternating harmonic series. So just take the regular harmonic series, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, so on and so forth. This is the series 1 over n from n equals 1 to infinity. We know that this series diverges from a previous section. But funny enough, oddly enough, this alternating harmonic series, so if we take all the same terms of the harmonic series, but then just change the signs on half of them, positive, negative, this series actually converges, believe it or not. Okay, so that's what an alternating series is, and then we have the alternating series test. It's how we can tell whether or not a alternating series will converge. So the way that we do this setup here is, for the alternating series test, what we're calling b sub n, so this b sub n term right here, that represents just the positive terms, like the absolute value of all the terms. So in the case of the alternating harmonic series up here, if we look at this, the b sub n ends up being 1 over n. And the component that does the alternating, that takes care of the flipping of signs, that's just -1 to the n. This right here, -1 to the n, this is equal to one of two things. It's either equal to +1, and that's if n is even, and it's equal to -1 if n is odd. So you can kind of think of an alternating series as consisting of two main components. Two constituents make up every alternating series. There is the actual alternating mechanism, the term that is what achieves that flipping of signs, and then you actually have the component or the piece that gives you the value, the absolute value of each term, the size of each term in your sum. So what makes this number here 1/3 is 1 over n when n equals 3. But what makes this sign positive is the fact that this -1 to the n minus 1, when we evaluate it at n equals 3, we end up getting -1 to the 3 minus 1, so -1 squared, which is +1. So I would urge you to think of every alternating series as consisting of two very important pieces: the alternating component, and this may look different. It doesn't have to be -1 to the n minus 1. It could be -1 to the n. It could be the cosine of n pi, because a whole number multiple of pi, when you take the cosine of it, on your unit circle, that's just right here and right here. So 0 pi 2 pi, 4 pi. Those are all right there, and the cosine of that angle is always positive 1. So that could look different. Okay. So for this theorem, we need to have a sequence that is decreasing and converges to 0, a positive sequence that does so. Quick little note here, if we take a look at this, we actually have a little typo here. This should be n plus, this should be b sub n plus 1. Okay. So this right here is essentially saying that we have a decreasing sequence. So this is just a nice way of saying decreasing. And then, of course, this is saying the size of each term of the series goes to 0, so it gets small enough. Okay. So if there's really 3 things, you have to make sure that your sequence is positive. So all your terms are positive for this b, what we're calling this b sub n. That's why it's important to separate the alternating component from the b sub n. B sub n in this case is positive, and this is what takes care of the negative stuff. So if, after you take care and isolate the alternating piece and the term that dictates the value of each term, the size of each term, if that sequence b sub n is positive and it's decreasing and it limits to 0, then this alternating series using those 2 pieces, b sub n and then the alternating bit, that series will converge. So the proof, you can pause and take a look at. It begins on the previous page. Not particularly important to know this, at least to succeed in any usual Calc 2 class where you're not doing proofs consistently. So example 1, determine whether the following series converges or diverges. So there is exactly 3 things that we need to verify or check, 3 hypotheses for the alternating series test. So the first thing we want to check, well actually before we even do that, let's go ahead and decompose our given series. So we can think of our given series term as a sub n, and this a sub n is negative 1 to the n minus 1 times our b sub n, where b sub n is the positive part of that, what dictates the value. So for this b sub n, we want to know, is it positive? So first thing, b sub n is definitely positive. Number 2, is it decreasing? Yes, it is decreasing. We know it's decreasing because the numerator is not changing in size, it's constant, but the denominator is getting larger as n increases. And if your denominator is increasing, overall, that makes the fraction decrease. So number 3, we need to check, is the limit of this expression, b sub n, equal to 0? And yes, again, if the denominator is continually increasing, that makes the fraction decreasing. So eventually this will approach 0. So these are the 3 hypotheses for the alternating series test. So we can say by the, I'm not going to write it all out, I'm just going to say the alternating series test, the series that we were given, negative 1 to the n minus 1, all over 2n plus 1 from n equals 1 to infinity, converges. So alternating series test is usually fairly quick, unless your series term is written in some way that might be slightly convoluted and maybe not readily recognizable as an alternating series. So whenever you see something like we have in example 1, where we've got this negative 1 raised to some integer power, we definitely know this is an alternating series. Whereas if we have something like the series in example 2, it's not immediately obviously clear that it is an alternating series. But if you write out a few terms, or if you think about it in more of an algebraic sort of way, like what is this actual angle and where does this angle live on the unit circle as n increases, you will see that it is in fact an alternating series. So let's think about this. Our angle, so we essentially have an angle theta n pi over 2. So this is a whole number multiple of pi over 2. So on our unit circle, if we visualize this, we're starting at n equals 1. So n equals 1 is right here on the unit circle. N equals 2 would be 2 times pi over 2, which would just be pi. Let's see here. And the next term, when n equals 3, we're going to be down here. And n equals 4. Okay, so we can see that since this angle is pi over 2, or 90 degrees, if we're starting right here, we're just going to take these 90-degree hops each time n increments by 1. So we're just going to keep going around this circle counterclockwise in steps of pi over 2 or 90 degrees forever. So we have to think about the sign of these. N is not equal to pi over 4. I just noticed that. This should be n equals 4. N equals 4. So we have to think about what is the sign of all these angles. Well, the sign of pi over 2, or anything that is at this location, the sign is going to be 1. At these locations, anything that's pi or equivalent to pi, that's going to be a sign of 0. Sine of 3 pi over 2, or any equivalent angles, would be -1. And sine of 2 pi, or any equivalent angles, will, of course, also be 0. So it looks like whenever n is an even number, notice here, even and even right here, the sign of that resulting angle will be 0. So, to summarize here, the sine of n pi over 2 is equal to, let's see, it's equal to 0 if n is even, and then it's equal to plus or minus 1 if n is odd. Okay. So this makes it a little bit more complicated, because really in this sequence here, or excuse me, really the terms of this series, which is a sequence, but I want to be really precise here, the terms of this series, half of them are 0 because sine of n pi over 2 when n is even is just 0. So if we think about this, if we write the terms, we get 1 plus 0 minus 1. Oops, sorry, there's factorials here, right? Let's get those factorials here. So this is 1 plus 0 minus 1 plus 0 plus 1 plus 0 minus 1, so on and so forth. So here it's 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, 7 factorial. So you can see that all the even numbers for n, we have 0 coefficients, so that's correct. And then the remaining ones start at the top of our unit circle where the sine of that angle is equal to 1, and then it's 1, -1, 1, -1. So 1, -1, 1, -1. So now let's just simplify this. This is 1 over 1 factorial minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. We don't need to write out these zero terms. We can just omit them because that's going to help us with pattern recognition. Okay, so at this point here, can we find a new way? Instead of writing this in terms of sign, can we write this in a new way? Yes. We should be able to write this as, let's see, we definitely have a negative component, so or excuse me, an alternating component. So the first term is positive, so I could make this n, and I could put a 0 there, because 0 is an even number. So this would be positive, negative, so that checks out. Now let's get the other piece to work out. We need the denominator to be odd numbers. So this could be 2n plus 1 factorial. (2n plus 1 will always give us an odd number, because 2 times any number is an even number, and then if we shift forward, for instance, by 1, we will land on an odd, since even and odds are always adjacent to one another. So if 2n lands on an even, then its neighbor, either adding 1 or subtracting 1, will be guaranteed to be odd. So we just have to make sure that the first number we hit is 1. If we plug in 0 for n, we get 1 factorial. And we can check, if we plug in n equals 1, we'll get 2 times 1 plus 1, which is 3 factorial, which checks out. And n equals 1 into the exponent here will give us negative 1 to the 1, which is negative 1, which checks out. So we can rewrite this series written in some convoluted way in a way that's a lot more recognizable as an alternating series, and it's ready for us to make it into a or it's prepared for the alternating series test. So for the alternating series test, we always just want to make sure that this is 1. Well, let's go ahead and write down what we have here. We're going to say b sub n is, let's just go ahead and define it. B sub n is going to be 1 over 2n plus 1 factorial. So b sub n is clearly positive. B sub n is also decreasing. And 3, the limit as n goes to infinity of b sub n is definitely 0. Check, check, and check. So by the alternating series theorem, or test, the given series from n equals 1 to infinity of the sine of n pi over 2 over n factorial converges. Great. Example 3, determine whether the following series converges or diverges. Okay, so for this one, it definitely looks like it's alternating because this piece right here is a positive number, and this will alternate. So this is an alternating series. This term here is a positive number, and this, what's not clear here is whether or not this is decreasing. This expression here, the numerator is definitely smaller in size than the denominator, but they're both increasing at a certain rate. Now, each of them have this square root of n, but because this is double, that means the bottom will increase at a faster rate. So if the denominator of a fraction is increasing at a rate faster than the numerator is, then we will get a fraction that is decreasing as n increases. So this is decreasing, and does this limit to 0? That's the thing. So let's go ahead and just really quickly say b sub n is this. So if this is our b sub n, we've already sort of mentally talked about how this b sub n is positive. We've convinced ourselves of that. Our b sub n is decreasing. We've convinced ourselves of that. And then number 3 is, what is the limit as n goes to infinity of this b sub n? Well, if we are taking the limit of this expression as n goes to infinity, we can use the method of dominating terms. So if we use this dominating terms idea from Calc 1 when we're examining limits at infinity, then we can say that this limit is the same thing as the limit of the dominating terms, which are, from the numerator, the only term is the dominant term, so the square root of n, and in the denominator, our dominating term is 2 root n. Well, square root of n is in common, so it cancels, and we get a half. So while this term is positive and it is decreasing, its limit as n goes to infinity is not 0, it's 1/2. So after a while, these terms here will all have a value of roughly a 1/2. Well, if we add up, even if we're flipping signs, that's not necessarily going to converge. The main issue here is we can even just go back and back before we even learned the alternating series test, and we can just examine this as a regular old series. What's one of our tests? The divergence test. What is the limit? Just regular old divergence test. What is the limit as n goes to infinity of -1 to the n square root of n over 1 plus 2 square root of n? This limit does not exist. Half the time it's approaching positive 1/2, and the other half it's approaching -1/2. Because we get these two different values flip-flopping back and forth, this limit doesn't exist because it can't hone in on one unique real number. This is sort of indecisive, and it's flip-flopping between two different values. So this limit doesn't exist, and we know, independent of the alternating series test, that if you take a series and you look at its rule, its term, and you take the limit of that term, and it's not 0, then you definitely have divergence. So the fact that this limit doesn't exist, this implies, by the divergence theorem, that the series that we were given, n equals 1 to infinity, -1 to the n square root of n all over 1 plus 2 root n, diverges. So not only does the alternating series test not work because this third condition fails, if your third condition fails, that's essentially, this third condition really is checking for the divergence theorem. It's like a final little test. It didn't pass, therefore diverges.